So welcome to another episode of Open World Chat. I continue to be John Odom, and your co-host here, Jim Dandino, continues to be Jim Dandino. Say hi, Jim.
For the time being, we'll see how things go over the next couple of days.
Oh, we're going to have fun today. We've covered a lot of geeky stuff. We push ourselves as being a place for all things geek, but for the first time, we're going to get into that mesh where the geekery and the nerdery meet, and that's in the whole geek science world, which we haven't really touched yet. So we've got with us today Jeffrey Adkins, who is he teaches astronomy and physics at the Los Medanos College in California, and is the lead teacher of the Deer Valley High School ACE Academy. And I want you to tell us what that is. And then at some point also, I want to talk to you about your book, The Boy Who Skipped. But what's an ACE Academy? I want to know.
Its acronym stands for Academic Challenge and Enrichment. We were the first academy formed in our district. It's evolved several times over the years. It's originally like a science academy. And we tried to broaden the scope a bit. So we're sort of an umbrella organization for all the things where kids don't have somewhere else to go. Our district likes to have academies. We have a business academy, a visual performing arts academy. There's an engineering academy at another high school. And it occurred to us there's a lot of the kids who want to do things that there is no academy for them. For example, if you want to be an English teacher, if you wanted to be a writer, there's no academy for you. If you wanted to be an astronomer, which is my big thing, there's no academy that's specifically designed for you. I just have a class, not a whole academy. So we designed ACE Academy to sort of an umbrella organization to allow kids to sort of do independent studies. And we also have some defined pathways, or you might call them majors, in the high school sense. So we've established this and sort of collected everybody else under our wing. It didn't fit. It consequently became the biggest academy in our school because so many kids didn't fit into the ones that were pre-designed for them. So we do, our main thing is to get you college ready. We have to meet college entrance requirements to be in our academy. You have to do a public project of some sort involving research, although it can be about any topic that you're passionate about. So we've had projects where kids have written novels, books of poetry, done paintings, dance performances, science fair projects, engineering projects, public service projects, and something that takes a dedicated amount of time. You have to do it outside the classroom, and normal human beings have to see it.
Well, you're doing the astronomy thing, man. That's the gold standard for, or is it is physics more the gold standard for the geek science thing?
Physics is like the nuts and bolts and how does it work science. And astronomy is, I think, kind of the big picture. Why are we here and what's our place in the universe? So I think a geek would appreciate this point of view. From my perspective, we're just one little planet with little people live on a little dirt ball. And the people on this side of the dirt ball argue with the people on that side of the dirt ball. Give me your dirt. No, I want your dirt. Give me your dirt. And that's how they spend their lives, arguing over dirt. But there's a lot bigger universe out there for us to claim and to know about and to wonder what we're in. We don't spend very much of our effort, collectively as a species thinking about that. But from the perspective of an astronomer, that we are the only things we know of in the universe that can wonder why we're here and try to figure things out. And we're part of the universe too. So somebody famous once said, we are the universe's way of figuring itself out. If that's our mission in the universe, is to figure out why the universe exists and what our function is. You might think of astronomy as like the purpose of humanity, and that everything else that humans do, all the sports we play and the jobs we have and the entertainment we have, is to provide a society wealthy enough to allow astronomy to occur in the first place. So, everything's in service of astronomy, in my opinion. The entire collective society exists only to allow a civilization comfortable enough to allow astronomy the room to exist, so we can get about the actual business of figuring out why we're here. That's my big picture. And I can't think of a perspective that's perhaps more geeky than that. I don't know.
Works for me. Yeah.
I can't think of anything that's more geeky than that too. That's not meant to be a criticism. It came out sounding kind of like grumbly, but it's not at all. It's a very healthy perspective on the universe, right? And on like our role in it. And that warms my heart a little bit. So
well, kids get all freaked out and they're like, we're so small, they think that means we're insignificant. And we spend a lot of time on astronomy explaining to people how tiny we are and how tiny the universe, the Earth is, and how small even our own galaxy is. And they get the feeling like we don't matter. But, even today, as far as we know for sure, we're it. It's a terrible responsibility to think that we're the only ones until you know better. You
right. But like mathematically, we're not, right? Mathematically, it's incredibly hard to imagine that we are actually it with the billions of planets out there that could potentially support life similar to ours. And that's just with our limited perspective on what life is and what sentience is. If you expand it out to some of the wild stuff that's been in some of sci-fi books and, sentient gas clouds, silicon-based life forms, stuff like that, it could potentially be everywhere. Black holes that talk to each other, like in X-Men comics now.
I like to tell students it's like, if life is natural at all, there's a lot of it. If it's a natural process at all, there's life all over the place. But it's a great big universe. And so, while I have no evidence for any of this, it's just my opinion, right? Till you have evidence, you just have an opinion. Right. It's maybe an informed opinion, but nevertheless, it's an opinion without evidence. So I am pretty convinced there probably is life in the universe somewhere beyond our own. And I'm equally convinced for similar reasons that it's never been here. It's the same logic. Right?
You introduced the idea that maybe life is unnatural. I like that.
Well, it could be. I mean, we don't know everything. And, you got to be kind of humble in this business and realize you don't know everything. There's a lot of things you don't know. Could there be silicon-based life form? I don't know. Could be. And we would, when it shows up on your doorstep, you'd have to change your theories of how life functions and you'd learn a thing. And I'm not saying it's likely, but it's an arrogant thing for any scientist to say that we've reached the end of knowledge and we know all things that can be. So you'll often hear us softening our language and saying things as far as we know, based on current theories. The preponderance of evidence is. So a wise scientist, in my opinion, never says it is incontrovertibly always true. We've definitely proven this for all time. Amen. Carve it in a stone, put it on a mountain. We don't talk like that. That's not real science. Because you're acknowledging with a humble attitude, we don't know everything. And although it may be very unlikely, we've been surprised in the past and we expect to be surprised in the future.
We always want to hedge your bet, right? I'm trained as a penetration tester, and first thing they tell us is never tell anyone that something is unhackable.
Right. That's exactly what I mean.
Yeah. So you have a professional interest in paying attention to this stuff, the maybe not the cutting edge science, but the latest news and the latest discoveries. What's the wildest stuff you've seen coming out of the astronomy field in the last couple of years that you think is that is maybe being undersold a little bit, right? Like we've all seen the pictures from Webb that are fantastic. We keep getting trickles of news in from Mars about more water and broader, the water's more spread out than we thought. But like, what are we not seeing that should be exciting people?
Well, that's a couple things I would put on that list. One would be we're able to do things about black holes we never dreamed we'd be able to. For right now, I don't know if you know, but we have a gravity telescope. It is able to detect gravitational waves that pass through space that we theoretically knew should exist. And we've built 2 gravity telescopes to independently verify each other. And we've now detected, a dozen cases where black holes have merged together and caused this tremendous pulse of gravity to shoot out through the universe, and it washed over the Earth, and we were able to detect it. So we're getting a direct measurement of the black hole itself. Usually, since black holes don't emit light by definition, you can't really see them. We always see their side effects. They're tearing something up and we see light coming off of the thing they're destroying, but we never can see the black hole itself. But for the first time, we're getting data directly from a black hole as it is causing a disturbance that emanates from its vicinity out into the universe. And this gravitational wave is now detectable. So that's a big deal to me. We're actually, we're detecting more black holes than we knew existed. We're getting, up to statistical level of information about what happens when, black holes merge, they get bigger, the event horizons grow larger, it's like a thunderclap of gravity just shoots across the universe, and we're able to detect that. Similarly, I think we're not getting a lot of press about the fact that, when I was in high school, we didn't even know for sure that there were planets in other solar systems. We didn't know. We assumed, everybody believed it to be true, but we were unable to detect them in any way. It wasn't until the 1990s that we were able to detect planets in other solar systems. And since that time, tens of thousands of them have been detected and confirmed. And we're actually building up statistical models of groups of them. There's unsolved mysteries about these planets. And then we're able to detect their atmospheres. In a few cases, we can detect water in their atmospheres. We're just now able to detect in the first cases of detecting moons around planets and other solar systems. So, the fact that we're able to do this at all is all, for me, I thought it would be hundreds of years before we could, get a space probe to Alpha Centauri and look for planets. I had no idea that the technology of cameras would advance to the point where we could literally detect them, and then do it lots of times. So we're developing more unsolved mysteries about these exoplanets that we didn't know. For example, the existence of hot Jupiters, according to our theories of thermodynamics and gases, they should not exist. These are planets that are as big as Jupiter, that are closer to their sun than Mercury is. So they're very hot. And this hot temperature should accelerate the light gases in their atmospheres until they reach escape velocity, and they would lose all their atmospheres. I did homework problems about this in college, where we were theoretically calculating that such planets should not exist. What we've discovered is that not only do they exist, there's a bunch of them. So there's a big fat unsolved mystery. How do these, there's something fundamental we're not getting. We don't understand. It's either that we don't get how the gas laws work on and making the atmospheres escape into space, or the planets are one of the only working theory. You have some kind of chaos theory thing where they form elsewhere and they somehow mysteriously, get perturbed in their orbit and come close to the sun for a while. But, all the orbits we're detecting are quite circular, which means they're very old and there's a lot of them. So it's not that rare. So the whole chaos idea is not really sold on me right now. So I would treat it as an unsolved mystery. We don't know. Nobody knows why this thing.
So the elliptical orbits kind of reduce the ellipse.
Well, if you have a bunch of big objects like big planets in your solar system, they all pull on each other. And if they do come close to each other, one of them would likely be ejected. So, over time, they'll tend to circularize. If they're really close together, they're not stable. They get ejected from the system. Two planets pass by each other really close. The big one will slow down. The small one will shoot out faster, like a gravitational flyby thing. And you might even lose a planet, right? So whatever's left has to be pretty stable, because if it was not in a fairly circular orbit, it would have already been perturbed and disturbed a long time ago. So it's like kind of a filter. It tends to preferentially accept, planets in stable circular orbits are more likely. Comets, on the other hand, they move so slowly, they have so little mass, they have all kinds of crazy orbits. That doesn't apply to comets, but it mainly applies to bigger things.
I was thinking they were getting captured, like Planet X is eventually going to do here, right?
Yeah, I think that, if there is one, it'll eventually have a reasonably close encounter with something and get captured or ejected or something.
What sci-fi series are you most into that has the best science?
What does it right?
Well, I'm a Star Trek guy from way back. I used to watch it in reruns at midnight when I was a kid, when parents wouldn't let me watch it. So I'd sneak out of bed and go watch Star Trek at midnight when it was first in syndication. And, there are elements of good science in Star Trek, but like a lot of other, commercial properties like that, they'll make up a rule here and there to fill a plot point. And there's a lot of made up technobabble, elements that don't really exist and things like that. But at least there's some lip service to the idea of trying to be consistent. You don't have a lot of, magical technology or plot points that pop up at the end to what's possible. They follow some rules. Star Wars, on the other hand, they just change the rules whenever it's convenient, and the Force gains a new power with every movie that you thought everybody should have had it, but all of a sudden they don't, or they do. So, they just kind of let it change to fulfill the plot of the moment. And so you can't predict. The rules are not nailed down. You know what the rules are. So, though, from a hard science perspective, scientists like hard science fiction because it's a lot like what they do for a living. Because when you're a scientist, you discover a new thing, and then you want to play a game where you play out the logical consequences of that. If quantum tunneling does exist, then what does it mean, and how can I use it, and what does it cause, and what would happen if I did this? And you make a prediction and you do a test and it comes true. So you've got this new thing, like a new toy, and you play with it to see how it works. In science fiction, you do the same thing. You take a rule that exists. Say, for example, we can't travel faster than light. But what if we could? You break one rule, you break it, you give them a warp drive or something, and then you play out the consequences of what that would cause. A really good example of that, I think, is in one of Larry Niven's stories about flash mobs, where he says, okay, suppose we have teleporters all over the planet, and they exist, and you can use them. They're publicly available. They work like phone booths. You dial up the destination, and you're there, right? Well, if there were such things, then you'd get a thing he called a flash mob, because if something exciting happened in the news, everyone would teleport there all at once. And there'd be this sudden, unexpected, giant mob out of control, right? And we're seeing similar things happen with social media now, sort of foreshadowing that, where people hear about stuff on social media and then they all go to a place and suddenly there's this giant mob. It's just not instant with teleportation. But Niven came up with the idea, if teleportation existed, what would be the consequences of it? And you take it and you run with it. And then you don't break any other rules. You break one rule and you run with it and see the consequences. Just like a scientist discovers one thing and you take it and you run with it to see the consequences. That's why scientists like hard science fiction, because it's like their work. So to answer your question, finally, I think that series-wise, I'm pretty fond of The Expanse. I think there's a lot of good science in there that, they don't try to break too many rules. They break rules like everybody else, or it wouldn't be science fiction. But, there's a lot of lip service, not lip service. There's a lot of respect for the laws of nature as we currently understand them. And there are consequences for you trying to, break those laws. And there, things happen that you can calculate out and get a prediction that would match what happened in the show. The Martian, the movie, is like that, where, everything is at least plausible. There's very little in the movie that could not possibly happen, but, the guy taught himself interstellar navigation so he could figure out the answers and write the plot. So Andy Weir did that. And so I like the Martian's good. I think as far as series go, I think I'm still a Star Trek guy through and through. I know that a lot of people who don't like this series or don't like that series for whatever reason, I love them all. I watch them all, and I think there's value in all of it. I think philosophically, that's what's appealing to me. Not so much the hard science in it, because, they make up stuff too, but the philosophy of it appeals to me. The optimistic future, the fact that we might figure out how to get along better when there's more power and cooperation than there is in conflict. There's a lot of positive messages in Star Trek, and we need it now more than ever, in my opinion. So
I think that's part of the resurgence lately is we don't have a lot of optimistic sci-fi in our lives right now, and we are barreling towards dystopia. And so I think that there is a generation of people that are making the shows now that are like, why don't we do something hopeful? Why don't we do something about a bunch of different people working together and be positive about what can be accomplished? And they're getting really good stuff out of it. We don't go an episode without talking about how good the new Star Trek shows are, but they're all at least entertaining.
Yeah.
And without Star Trek, as our utopian fiction, the closest other thing we have to utopian fiction, honestly, I think are the superhero movies where the rules get broken. You can break the rules and things can things can work out, but that's it. And that's not utopian fiction. It's just a sort of cousin of it. And Star Trek is giving us what we want there. It's great.
Yeah, there are consequences. I know that we can kind of reverse them sometimes and undo the snap, and Spock can come back from the dead. But at least for a while, there are real consequences to your decisions in these shows. I think you kind of hit the nail on the head. It's just like superhero movies are a modern mythology. They're directly parallel to the myths we told for thousands of years. So it's not necessary for us to nitpick them to the point where it's like the physics doesn't work and so on. And all that stuff. I mean, it's fun to do, but it's not necessary to enjoy the movie and to get something, hopeful out of it. And the good guys win sometimes, and it's okay for the good guys to win. So I think that's the thing that's really appealing to me for both of those genres.
It's wild to me, though, about Star Trek and Star Wars is that are we possibly closer to Star Wars technology than we are to Star Trek technology, at least in terms of the engines? Because don't we have a working model of an ion engine like in testing? And
we've actually we've built ion engines, actually use them. They've been like in space. There's a mission called the Dawn mission, and it was an asteroid reconnaissance mission. It went from one asteroid to the next in the asteroid belt and would orbit them and take pictures, and then it would move on to the next place. And it had an honest-to-God ion engine that would push for months and months and months with this kind of weak thrust, whereas a chemical engine burns for 15 minutes and runs out of gas. So we've had a couple of missions that have used the ion technology to create thrust, and they've been successful. They are not good for humans because the thrust is so low. It would take forever to get anywhere. So they're better for long-term deep space missions that can be run on electricity, like a small nuclear reactor or solar power. They require high voltages to run. But so we do have ion thrusters. They do work, and we've used them, and both in experiments and actual missions. But as far as warp drive goes, it's just like, it looks fun on paper and nobody has the first freaking glue. We don't know. It's not a question of money. There's no underlying physical theory that would allow us to build one no matter how much money we had. We don't know even if it's possible to build one, and if we wanted to build one, where to even start. It's like it would be nice if it existed, but we don't. It's like, I can't even at this point claim to you that it will ever even be possible ever, because we're sort of like saying to a caveman could perhaps understand that a bird can fly, and then could extrapolate the idea that with assistance a human could fly, and then using fantasy thinking could imagine a day in the future when humans could go to the moon, right? They don't know how to do it, but they could say to you, I could see that someday people might figure that out. I don't see at this point, and again, giving that caveat that we don't know everything and there are things yet to be discovered, and we could, like, somebody could make a Zephyrin Cochrane moment and have that flash of inspiration and teach us all new physics and change all the laws, and we have to rewrite our books. And yeah, it could happen because we don't know everything. But in the context of asking me, how likely is it? I have to professionally say it's not likely at all, because we don't have the first clue about how to even start building such a thing.
There's this mathematical physics construct, though, that's out there that people refer to as warp drive. And they love it because it involves a bubble, like a warp bubble, like the way they talk about. I was going to try to ask you a smart question, but I'm not going to. I'm just going to say what
I know exactly what you're talking about. It's like,
yeah,
I don't know how to pronounce it. The Albuquerque drive. I don't know how to pronounce it.
Yeah.
Right. It's the one that Seth MacFarlane talks about on his show, right?
You increase gravity in the front of the ship and you pinch space, and then it's like a zipper unfolding behind you, and it flings the ship forward on gravitational.
It's all great
waves.
on paper, but it requires the existence of a kind of exotic material that you would need to make it happen. And we don't have that stuff. We don't know how to make that stuff. We don't know where to find that stuff. If it existed, you could build the drive. But that, it's like saying, I have a gasoline powered car, but where do you get gas? And I don't know how to make gas. I don't know where to get the stuff to make it go. It wouldn't do any good to give a caveman a car because there's no gas, right? So by analogy then. So yeah, I mean, the paper has been written and it describes how you might build a warp drive if you had this magical, unknown, mysterious, exotic matter. If such a thing existed, you could put it in a box and make a warp drive. But it's sort of like the dilithium crystal, you might say. We don't have that, and we don't know where to get it. So I'm not saying that it could never be done, but right now, all the money in the world would not give you any progress. There's just no way to solve the problem.
So it's all about MacGuffin matter. We need to discover MacGuffin matter.
That's MacGuffin matter. That's exactly what it is. So We haven't had, the whole idea here is back in the 1800s, Maxwell unified static electricity and magnetism, which used to be viewed as separate things. And so he wrote a series of equations that explained to us that you can use one to make the other. And all of a sudden, technologies just exploded on these equations. Marconi invented the radio because he was able to send a signal with the electromagnetic waves. So you can use the one to make the other. And the unification of these two forces led to a technological revolution. Oh my gosh, it's the greatest thing ever. You can use electricity to make magnets. You can use magnets to make electricity. You can go back and forth and use one to create the other. You made motors and generators and speakers and microphones, and it led directly to our technological society. So the thinking is, if you could marry those two forces together, what would happen if you could marry electricity and gravity? Then you could make gravity with electricity and gravity plating, gravity drives. You could make those things. The issue is there's no theoretical or experimental basis for knowing how to manipulate electricity with any kind of technology that would ever have. We've never detected any kind of gravitational influence from any electrical device we've ever built. So, if such a thing existed, if it's even theoretically possible, is unknown. There's no theoretical equation waiting in the back. Like Maxwell had the equations to connect the two. We don't have a Maxwell's equations for gravity. Einstein tried to figure it out, couldn't do it. We haven't unified gravity to the point where we can manipulate it with other forces. So that means we can't create that kind of warp drive that we'd like to, where we were able to manipulate gravity on demand. You can imagine, in the science fiction sense, okay, let's pretend we can and then run with that. But in the real world, if people could build a gravity plating or a zero gravity room or something that would even just affect it by 1%, they would be doing it right now because there would be a use for that. But we don't know how to do that. That's the gist of it. The whole argument in the science fiction realm depends on the idea that we don't know everything, and perhaps some genius will figure out a way to build a device that has twisting magnetic fields or static charges flying through it, and some particular combination will magically transform itself into gravity. But there's no equation to govern that, and there's no theoretical underpinning to predict that it should be possible. It's just a fun idea from our perspective. A lot of things we do today would have been possible in the past, and again, we don't know everything. Somebody smarter than me and smarter than all of us could figure it out one day and then teach us how to do it. And then we'd have a thing. I don't mean to be a downer, but that's just the reality of it.
No, not at all.
You seem like you answer these questions for kids a lot. So it seems like you've got it pretty comfortably on lock. Well,
I got to take the point of view of in science, we often say when there's an argument, reality wins. You have to let reality win. That doesn't mean you stifle your imagination, because if you thought that we figured everything out, you'd never find out anything new. You stagnate. You have to question. You have to doubt. You have to go beyond what's written down in books and accepted by the mainstream. Where that doesn't mean that every idea you come up with is eventually going to become true. But occasionally that does happen, and you have a breakthrough, and we learn a new thing. Einstein didn't think quantum mechanics was a real thing. Thought it was a mistake, and now we have technology based on that. So, obviously we can learn new things, and we can be surprised, and we can discover areas of science that we didn't even know existed, and it causes effects. It allows us to do things we couldn't do before, like miniaturized computers are impossible without quantum mechanics. In the 50s, computers the size of office buildings, because the switches were big enough you could see them with your eyes. So using quantum mechanical concepts, they invented the transistor that enabled us to have microcomputers and smartphones and things. So we didn't even know that was possible. We imagined it, but in the 50s, no one knew how to make one, and didn't know that 50 years later we'd have figured it out. So, it's conceivable we'll figure it out someday.
Right.
Yeah.
The gravitational waves that they detected, what rules are they bound by? Are we seeing them? Do they travel slower than the speed of light? Are they just kind of washing up on us right now? Or is there, when two black holes smash into each other, does something move faster than we suspect they should be allowed to move?
Not in that case. Gravitational waves do propagate at the speed of light. Basically, I can actually use a superhero analogy to explain gravitational waves, I think. So, back in the olden times, Superman was a lot stronger than he is now. He could move whole planets. He'd shuffle planets around and stay like had effectively infinite strength. So imagine the Superman's floating in space. He flies up to this uninhabited planet and he grabs a hold of it and just moves it towards you. And then he moves it towards you and pulls it back. And then you're off at some distance in a spaceship floating, watching him do this. When he moves the planet closer to you, the gravity of that planet is now stronger because gravity is stronger when you're closer. So in your floating spaceship that's not touching this planet, you'd feel a tug towards the planet, right? And then when he pulls it back, the gravity weakens. So that would have the effect of shaking your little spaceship because he's moving this planet back and forth like this. That would make your spaceship shake, right? In response to those changing waves of gravity, it would reach you. Gravity stronger, then it's weaker, then it's stronger, then it's weaker, then it's stronger. So the effect of it would make your spaceship wiggle. So you're receiving the gravity wave that's being generated by Superman by shaking this giant planet enough to change the gravity. And you can't have a bigger source of changing gravity than a black hole. So when they merge, there's this huge gravity shake, and it travels through space at the speed of light, like everything else. So when it gets to the Earth, it hits a laboratory that stretches it and compresses it and stretches it and compresses it. And that's essentially what we're detecting as the wave passes over. And we have two of them, so we can double check that's not some sort of mistake. So they both receive the same signal. We know it came from space. It's not some truck driving by the laboratory or something. The building is shaking because it's being stretched by this gravity wave. And there's two different ones. I don't know, there might be more now, but initially there were just two.
Is there a Doppler effect?
Sorry?
Is there a Doppler effect with the gravitational waves?
That's a good question. The Doppler effect would have to happen because the source is moving. So if both black holes are moving towards you, the waves would arrive more frequently. I would say the Doppler effect would occur with a moving source of a gravity wave. Never seen anything, like formally written up about that, but it makes sense. I think you probably would have the Doppler effect could happen with a gravity wave.
Oh, there you go, Jim. You did it.
I did it. I solved science. Good night, everybody.
Should write that up. Letter to the Astrophysical Journal.
I already got it, but you need to jump on this, okay?
Yeah, there you go. It's all you now, Jeff. We're counting on you. Run with it. You were talking about the speed of light. When is the speed of light not the speed of light? There's
a word, superluminal.
Mm-hmm.
There are a few things in nature that appear to be superluminal. For example, if you have a quasar, as a black hole that's chewing up a whole galaxy, and stuff that doesn't actually fall into the black hole gets spit sideways before it crosses the event horizon, it can come out in this jet. And if that jet is aimed at your face, you have a quasar. So if the quasar is slightly off axis and it's pointing at you at an angle like this, there's a relativistic illusion that occurs that the distance it travels compared to the time it takes appears to make it go faster than light. It turns out, however, it's a relativistic illusion. It isn't really physically traveling faster than light. It's just because the relativity effects are tricking you. I don't know how to do the math, but I do know that somewhere in the world, people have explained this apparent superluminal velocity. It isn't real. So another thing you can imagine traveling faster than light, like imagine that you take a flashlight and you shine it on the wall and you move the flashlight to the side, right?
Mm-hmm.
So the shadow or the light that's on the wall that moves across the room goes pretty fast. Now imagine you take a flashlight, a giant laser, and you aim it at the moon and you just flick it across the moon with your wrist, like that. So the spot of light would actually cross the moon faster than the speed of light. It could do that. But the issue is you're not actually taking any information from the left side of the moon and delivering it to the right side. So information cannot travel faster than light. But you can create a moving spot that's not a physical object. It's just the presence of photons here. Other photons show up here. Still yet other photons show up there. And you can make that spot move faster than light, but it doesn't do you any good. You can't use it for anything. You can't send a signal from the left side of the moon to the right side faster than light because there's no way for you to influence that signal that's on the left and make it carry new data to the right. It's all coming from you on the Earth, Mm-hmm. So you can kind of do some tricks like that make the illusion of traveling faster than light, but the theory is quite sound. I mean, if anybody could disprove Einstein for 110 years now, they would have done it because it would make you famous. I'm smarter than Einstein. And every single experiment that has been done to disprove relativistic effects has failed. They've all failed. People have been trying for 100 years to crack that open and show that there's a logical error and exception of this or that. Every single experiment has failed. we have completely verified that relativity works the way we've been describing it in books. It really does happen. Time travel is real. It's just, it doesn't work the way it does in the movie, but it does happen. And there's even been a guy who had an RV, put an atomic clock in his RV, put one in his garage, drove off for summer vacation, came back home, and the clocks didn't match because he was driving around. So it's a very small effect, but we can detect it because our clocks are really good.
Oh, I've got a question I've got to ask because it always drives me crazy. And it just occurred to me, and I'm so glad I thought of it. The black hole time dilation effect, right? And people are experiencing it. They get close to it and they go back, and, you know, their kids have grown up or that kind of thing. Could you get close enough to a black hole to experience an effect like that we see in sci-fi without getting strung out into spaghetti?
Yes.
Good.
You can calculate it. The thing that I have a problem with the movie is that they're little spaceships. It's just a magical, almost infinite fuel supply, and they can actually fight that intense gravity, land on the planet, blast off several times, and leave. You know, it would take a tremendous amount of fuel to be in the vicinity of a black hole, the gravity strong enough to cause those effects. So they kind of slough over that. You know, like we got these advanced rockets. That's the issue for me. But the physics of the time warp, definitely works. It turns out surprisingly that the bigger the black hole, the easier it is to experience that effect. So if you have a small black hole and you're coming close to it and you're getting that intense gravity, the small black hole, your feet are closer to it than your head is, and you get that spaghettification stretching effect. You get killed. It tears you to pieces. And so by the time you get enough gravity to cause the time warp effect, the black hole has torn you to pieces and killed you. Okay. But if you have a giant black hole, like a tremendously huge one, like say one at the middle of the galaxy or something, then as you approach this giant black hole, there's enough gravity to cause the effect. You get the time warp effect, but the distance from your head to your feet is minuscule compared to the distance to the black hole, which is much bigger. So the stretching effect doesn't really occur until you're pretty close to it. You actually, to get stretched apart and killed, you'd have to go ahead and cross the event horizon, go down deep into the singularity near the place where the warp happens, and then you'd be killed. So you could, theoretically cross the event horizon of a really big black hole, and you'd survive. You couldn't get back out again because you can't go faster than light, but you would survive the transition. You could see what's in there. Maybe there are other ships trapped in there. Maybe there are planets orbiting the black hole under the event horizon. It's nobody really knows what's in there. We can just speculate and guess because there's no way to get information out of the event horizon for us to look at. We'll never know because, we can't go faster than light. Now, the Enterprise, if you had a ship that really did have a warp drive, theoretically should be able to cross the event horizon, look around, and then leave again because they can outrun light, and that would enable them to cross the event horizon. But for any like ship in our real world, if you cross the event horizon, you're doomed, you're trapped, you're never coming out.
So I know we're getting close on time here, and I wanted to make sure before we disappeared that we had a chance to talk about your book, The Boy Who Skipped.
I assume that that it exists because you asked me about it.
Yeah.
So, you're in an elite group of people that actually know that book exists and maybe have even looked at it. The story is really kind of two or three things happening at the same time. It's about my freshman year in high school, and some of the experiences I had in the theater program in high school, and leading on up to Wilderness Road, which you know about. As an outdoor drama, it was in Kentucky, based in Berea College in Kentucky. It doesn't exist anymore, but at the time we would have a show throughout the summer, outdoor theater, and there's a musical about the Civil War. So the other part of it is about my high school teacher, who in real life is named Carol Combs, and she was an inspiration to me as a high school student and taught me the value of hard work and persistence and being able to take criticism and be able to move on and not take it personally and deal with it and become what it means to be a professional in something. So, and it was a really inspirational thing for me. And then it was also the fact that I was hopelessly head over heels in love with her niece, and she was older than me, and it was never going to happen, but I wanted to think about it a lot. So all of those things happening at the same time. I have a lot of stories that I just sort of used to tell for many years, and I just kind of stitched them all together and wrote a book about it.
Yeah, you're one of these people we have on who can do all kinds of things. You talk the science. You wrote a book. You got a web comic going. You're just you're a man of many talents. And
it was I just I get latched onto a thing for a while, and I do that for a while, and I move on and do another thing. here's a story out of the book I think you'll find interesting. It's sort of how it starts, right? So I was in the 7th grade, and my principal came to the door and knocked on the door. Jeffrey Adkins come to the office with me, and all the kids would go, "You're in trouble," like they would, So I go to the office with the principal, and he says, "We're going to town." So he takes me outside, and we get in his car. And I said, "Shouldn't I tell my mom we're going to town?" "Oh, I already talked to her. It's okay." So there's no note, there's no form, I just get in the principal's car. We drive to town. It's about 15 miles away, and we go to this pool hall. And in this pool hall, there's like guys in tank top t-shirts and, smoking and drinking alcohol. And it's kind of a smoky, dingy pool hall. It takes me, I'm like a 7th grader. He walks me into the pool hall. We go in the pool hall, and he takes me to the back, and there's a couple of pinball machines there. And one of the pinball machines is open like this, like an alligator. And there's a dude inside of it. So he says, "Hey, here's that kid I told you about." And he says, "I got to go." And he leaves. So here I am abandoned in the back of the seedy pool hall. And the guy crawls out of the pinball machine. He says, "Come here, kid." So he takes me into the back, and in this little narrow winding stairway that goes up to the attic. And it's getting creepier and darker, and kind of, I'm starting to get nervous that something is not right here. And then when I get to the attic, it turns out it's filled with electrical equipment. And he says, "Here's a box. Fill it up, take whatever looks interesting, go home and play with it." So then he left, and I was, here's some batteries, and here's some light bulbs, and here's a multimeter. It looks scientific. It has needles on it. And I just filled up the box and carried it downstairs. And then the principal came back and took me back to school. And that was my GATE program. So, he said, "Well, you do science fair stuff. We think you can do some more stuff. And so I wanted you to have access to some equipment we don't have at school. So go home and play with us and teach yourself some electricity." And, that kind of stuff is kind of like what happened to me. A lot of stuff like that happened to me in elementary and middle school. And it's just a bunch of stories like that all stitched together in a book. It's available now for free at my website, astronomyteacher.com. And you click on projects, writing projects, and you can find a downloadable copy there. You can download and read it. So I posted the whole thing. It's been out for a while now, so I'm just kind of like interested in having people read it now. I'm not entertaining the fantasy that I'm going to sell 1 million copies anymore, but I just like people to read it.
Well, Jeff, thanks so much for talking to us.
We've got plenty of geek science that we can still hit. So
awesome.
We will hit you up.